Good evening. So last lecture we started with Bessel's equation and we used the Frobenius method to derive a solution. We started with the assumption that the solution is of the form am x power m plus r, where m and r is to be determined. And by equating coefficients of x power m on both sides, we came up to this, where am plus 2 is written in terms of am. And we also saw that for odd values of m, the value of am is just 0, so which means there are no odd powers of x. And you can take this relation, and instead of writing it as a relation between m plus 2 and m, you can shift the index and write it as a relation between am and am minus 2, which would be this. So if you have a power series y of x, which has only even terms, so you have a naught plus a2x squared plus a4x to the 4 plus and so on up to infinity. You can also express this as a summation which has this form, say m equals 0 and you have m equals 0 to infinity, where you can write, just for clarity I'll use k instead of m, k equals 0 to infinity, you have a2k x power 2k, where k runs from, k takes values 0, 1, 2, 3, and so on up to infinity. So we want to write this in terms of a counter or an index which takes values 0, 1, 2, 3 instead of it taking only even values of m. Okay. So for that we are going to write. You can do this like you can just say replace m with 2m if you are able to follow that. For some, they may prefer that they want to replace m with 2k, which would make this a2k equals minus a 2k minus 2 divided by 2k times 2k plus 2 nu. So you can simplify this a little bit and write minus a 2 times k minus 1 divided by 2 squared times k plus nu. Where k can take all values of integers from 0, 1, 2 and so on, but you will have only even powers. Okay.
Is that k minus one on a sub two? Is that in the subscript?
Yeah, it's on the subscript.
Okay.
Written a little bit. So let's just apply this to get the first few values. Like for example, by setting k equals 1, let's try to evaluate what is a2, which would be minus a naught divided by 2 squared times 1 plus nu. And you can also do, let's say k equals 2, a4 equals minus a2 divided by 2 squared times 2 times 2 plus nu. Easy enough. Now what you do is replace a2 in terms of the previous relation and get it in terms of a naught. What would that be? This will be minus 1 over 2 squared, pardon me being in the way, and then a2 itself is minus a naught divided by 2 squared times 1 plus nu. So this is a naught divided by 2 raised to the power 4 multiplied by 2 factorial times 2 plus new times 1 plus new. Obviously, we want to write any value of a to k in terms of a naught and something that appears below. Can you try to identify that pattern? Like we just did A4, we did A naught, I'm sorry, A2 and then A4. Maybe you can try A6 and see if a pattern is starting to pop out. What is A6? A6 would be minus A4. I have to substitute k equals 3 here. So k equals 3 will make this A4 divided by 2 squared times 3 times 3 plus new, which would make this minus A naught divided by 2 power 6 times 3 factorial 3 plus new times 2 plus new times 1 plus new. Would you see this and go, yes, okay, you follow this? Yeah, okay. So now the pattern is given in the book. I can just write down the formula, but can you try? Can you generalize this formula for any value of k? You had minus a naught, then you had plus a naught for k equals 2, and then minus a naught again for k equals 3. So what is the pattern? Minus 1 to the power k minus 1 to the power k multiplied by a naught. That is the numerator. You had 2 squared, 2 to the 4, 2 to the 6. So what is the generalization? 2 raised to the power 2k. 2 raised to the power 2k. And then you have 1 factorial, 2 factorial, 3 factorial, that's easy. We'll write k factorial. And then you have 3 plus new all the way back to 1 plus new. So this is nothing but k plus new, k minus 1 plus new, and so on all the way back to 1 plus new. So I have my solution y of x is now summation k equals 0 to infinity a to k x power 2k plus new, right? X power 2k, and then I'll have x power new. So that's okay. And a 2k itself is given by a formula minus 1 power k a naught divided by 2 power 2k k factorial k plus new all the way to 1 plus new. So I can write y of x equal to a naught. A naught is common in everything, so I can write a naught times x power new multiplied by k equals 0 to infinity minus 1 power k x power k divided by 2 power 2k k factorial k plus new all the way to 1 plus new. Yeah.
Do we have any idea about the value of the
No.
candidate?
We so far have not made any, we've just assumed that new one or like plus minus new is a real number whose difference is not an integer and it's not equal to 0. So we are with the case new is not equal to 0. That's a special case. We also think 2 new is not an integer. So new is not 0. Which means you have this to be one of your basis functions. Okay. So you can you have constructed a function with a naught is still undetermined. With me so far, a naught is still not known. All the while here, we have just worked with the equation. We don't know anything about the boundary condition at this point. Okay.
Why you did transformation from integer to k?
To make sure that this summation runs continuously and doesn't skip every other value. It's like saying you are counting from 0 but skipping every odd number and counting still to infinity. It still has an infinite number of terms even if you start from 0 and count every term. It's infinity. It's just at what rate you approach the infinity. Okay, so this term here, there is this function you have right here. This function you have right here is valid for any value of new which doesn't fall into these two categories. Any other value of new, this is fine. Okay. If you want to construct the complete solution, you need to have two basis functions, right? So when you look at this equation, what is the corresponding initial equation? I'm sorry, initial equation. So if I write this of the form y double prime plus y prime over x plus x squared minus u squared over x squared times y, my b of x is 1, my c of x is x squared minus u squared. So my initial equation is r times r minus 1 plus b naught r plus c naught equal to 0. This implies b naught is 1. This implies c naught equals minus nu squared. So I get r squared minus nu squared equal to 0 or r equals plus minus nu. I get two values of nu. That's what I'm trying to say here. By having two distinct roots for nu, which don't fall into these two categories. When we get to these two categories, it's a separate discussion. So to construct two linearly independent solutions to this differential equation, you can write y of x equal to c1 times y1 of x plus c2 times y2 of x. Where I can take this entire function and write c1 times x power nu or c1 times summation k equal to 0 to infinity minus 1 power k x power k plus nu divided by 2 power 2k k factorial k plus nu k minus 1 plus nu and so on up to 1 plus nu. This is one of the basis functions. Would you agree? I mean, we just got it through the entire solution process. So this is clearly something which can serve as a basis function. What about the other basis? What about the other linearly independent function? You can go through the same process and instead of nu being the value that you choose, you can replace nu with minus nu with the knowledge that or knowing that nu ain't 0 and 2 nu is not an integer. Knowing that these conditions apply, you can think of y2 of x equal to, I'll call that a naught multiplied by summation k equal to 0 to infinity minus 1 power k x power k minus nu divided by 2 power 2k k factorial k minus nu k minus 1 minus nu and so on up to 1 minus nu. Now, if I make the assertion, that this y1 of x and this y2 of x are linearly independent, would you agree with me? Would you disagree with me? You have to do one of the other. Either agree with me or disagree. Not sure is not an option. Sorry? They are independent, and how will you prove that?
The ratio of.
Should not be a constant. So if you consider y1x over y2x, you can easily prove this is not a constant. This is a infinite series with terms which are x power nu, x power 2 plus nu, 3, 4 plus nu, and so on. This would be a term. Wait, I made a mistake here. This should be x power 2k because we can have only even powers. So this is a nonlinear function because you are multiplying with x power nu, and this is another nonlinear function because you are again multiplying with x power minus nu. And if you take the ratio, it is easily seen that it's not a constant, which makes y1 and y2 of x are linearly independent basis functions. Here is where you can see why, if u were to be 0, then y1 of x and y2 of x, y1 of x and y2 of x are not independent. In fact, they are equal to 1, means this ratio is equal to 1. And when we were doing the derivation, at one point we assumed that 2 nu plus 1 times a naught is equal to 0. So we assume that 2 nu is not equal to minus 1. So that is the other condition, that 2 nu is not an integer. So this is an important statement here. In fact, I think this problem is on the mock exam. For new values which are either not 0 and 2 nu is not an integer, the general solution is y of x equals c1 y1 of x plus c2 y2 of x. You can drop this a naught from here because that is absorbed into the c2. So this will be c1 summation with the large terms x power 2k plus nu plus c2 summation x power 2k minus nu. You can fill in the blanks. Good practice. This is the complete solution for Bessel's equation for distinct values of nu. Still, we haven't made any assumption about whether nu is an integer or not. That comes next. Well, not necessarily. If say nu equals half, 2 nu becomes an integer. Nu is not an integer.
Yeah, but you can't be an integer.
What about 3 halves?
That's not, makes it integer, I thought.
That is, those cases are not covered by this solution. I didn't say 1, I said integer.
Yeah.
So if nu is 7.5, this still is this condition is still met. With are we together so far? Yeah. Okay. So then we jump on to the next special case. We start discussing cases one by one. What if nu is an integer? We jump directly to that. Let's say nu equal to n, an integer. Obviously, if nu is an integer, only one of these functions can be used as a basis. Why? Because the other becomes linearly dependent. So we are going to take a short detour from constructing the general solution. You can always take that the first function is always a basis. It can be used as a basis function, but for the special cases we are going to discuss, the second function has to be something different. Okay, but before we take that, before we go there, the detour is, let's look at the properties of these polynomials, of these infinite series, when nu happens to be an integer. And this is where we come to the very famous Bessel's functions of the first kind. So let's start with the discussion. Nu is an integer. Start here. A to k is equal to minus 1 power k a naught 2 power 2k k factorial k plus n k minus 1 plus n and so on up to 1 plus n. A naught is just some constant which we don't know about, but to derive some derive some compact forms, let us choose A naught is equal to, obviously I didn't come up with the choice, that's why I have to look up, 1 over 2 power n times n factorial. If you do that, I'm going to write it and then ask you, this becomes minus 1 power k divided by 2 power 2k plus n k factorial k plus n k minus 1 plus n and so on up to 1 plus n times n factorial. What happens now?
K plus n factorial.
If you read this together, you would recognize this k plus n. You would recognize this as,
K plus n factorial.
everybody does that? Do you recognize this as k plus n factorial? Right? So this becomes k plus n factorial. And why is it okay to choose a naught to be a specific value? Why is that not a problem?
Have another position. Important.
The C1 will automatically adjust itself to take a specific value which satisfies the boundary conditions. Okay, so we are going to write a to k is minus 1 power k divided by 2 power 2k plus n k factorial times k plus n factorial. So our y1 of x, which is c1 multiplied by x power nu, which I'm going to write x power n, multiplied by k equals 0 to infinity minus 1 power k divided by 2 power 2k plus n k factorial k plus n factorial, where c1 is arbitrary. Actually, what I should write is c1 times y1 is this. So I'm going to say define Jn of x, Bessel's function of order n, to be x power n, or I can write summation k equals 0 to infinity minus 1 power k plus, minus 1 power k times x power k plus n, 2 power 2k plus n, k factorial, k plus n factorial. This is what we call Bessel's function of order n. So far, I haven't made much discussion about convergence. When you write an infinite series, the expectation is all of these infinite number of terms will add up to a constant, so that it's a finite number. If each successive term keeps growing, it means that number will eventually become too large or will approach infinity. For this function, you can easily check the higher coefficients, that is x power 4, x power 6, and so on, will rapidly go to 0, because in the denominator you have a large factorial which becomes bigger and bigger, making the whole term smaller and smaller. In other words, this is a convergent series and it's very easy to check. We don't really delve too much into divergent series or series that have slow convergences. Most of the infinite series or the problems we have seen so far, if you check, it would be rapidly convergent. So we didn't make that an issue. Okay, but good to be aware of what is convergence. All right, so I would like you to try writing out what is j naught of x and j1 of x, and this brings us to one of the problems to prove that identity. Derivative of j naught of x is minus j1 of x. We can try that. Okay. So first let's start with j naught of x, where you have to set n equals 0 here, which will make this summation k equal to 0 to infinity minus 1 power k x power k divided by 2 power 2k k factorial, k plus n factorial. So this is another k factorial. And if I write it out, this would be 1. And then for k equals 1, this is x power 2k. I keep missing that. So 1 minus x squared divided by 2 squared is 4. Yeah, 1 minus x squared over 4. Then third term is k equals 2. That will be plus x to the 4. 2 power 4 is what? 16. 16 times 2 times 2, 64. You with me? You're okay? Right? We'll write one more term. K equals 0, 1, 2, 3. So that will be minus x power 6. 2 power 6 is 32. 32 times 3 factorial. 3 factorial is 6. So we need 32 times 36. Who's strong in arithmetic to quickly tell me that? Okay, good, thank you. 1152 and then plus and so on up to infinity. It's just some practice. This is the first time some of you may be seeing this, so I'm just asking you to write it out. And then J1 of x, by setting n equals 1, we're going to get J1, which would start with k equals 0 to infinity minus 1 power k, x power 2k plus 1 divided by 2 power 2k, k factorial, k plus 1 factorial, which is first term is going to be x. This is 2 power 0, 0 factorial, 1 factorial. So first term is x. Second term, k equals 1 will be x cube divided by 2 power 2 is 4, 2 squared is 4, 4 times 1 factorial times 2 factorial, 4 times 2 is 8. Plus x power 5, 2 squared, 2 power 4 is 16, 16 times 2, 32, 32 times 6. What is 32 times 6? 192. Right? 32 times 6. Yeah. Minus and so on up to infinity. So in one of the mock exams, I posted 2 mock exams. In one of them, you are asked to prove J naught of x derivative equals minus J1 of x. Not super complicated. Either you can work with the infinite series or you can work with the summation. Either way, it's like a couple of steps. Can you please do that? I left my water bottle outside. I'll go get it. Fun fact, I have had water bottles left in the hallway for like up to 10 days and nobody ever touched it. Either our department folks are too good or they just don't lift their heads up from the floor. Okay. Let's get J naught of x, or derivative of the Bessel's function of order 0, which would be minus 1 power k, x power 2k minus 1. So if k equal to 0, this would be a problem, right? Yeah, we'll have to start from k equals 1. Divided by the rest of it, 2 power 2k, k factorial squared. So you have this. If you want to match this with j1 of x or minus j1 of x, let's shift the index by 1 unit. Wherever k appears, replace k with m minus 1. 1 second. Yeah, wait. M equals k minus 1. Yeah,
So if we differentiate the J naught of x,
yeah, with respect to x, yeah.
is with respect to x, so there should be one 2k term. And if
Right.
really,
2k.
yes.
I missed that. So I want to shift the index by replacing k minus 1 with m. So wherever k appears, I can replace it with m plus 1. Wherever k appears, replace it with m plus 1. What will this lead us to? Summation m runs from 0 to infinity. 2k, so I have 2 times m plus 1 minus 1 power m plus 1, and then x power, I have 2 times, or 2k minus 1 would be 2 times m plus 1 minus 1, which is 2m plus 1. 2m plus 1 divided by 2 power 2 times m plus 1 multiplied by m plus 1 factorial squared. So you need to show some of your algebraic steps to modify this, simplify this, and establish that this is same as this. How would you do that? I mean, you see this and you see this, you see a lot of similarities. What I would suggest doing first is stop calling it M. It's a name, call it K again, so that it's easy for you to pick similarity. Okay, so this is J naught prime of x equal to k equals 0 to infinity 2 power k plus 1 times minus 1 power k and then multiplied by minus 1 x power 2m or 2k plus 1 divided by 2 power 2k times 2 squared multiplied by k plus 1 factorial times k plus 1 times k factorial. Or if you want, I can write it the other way, k plus 1 factorial. So obviously this minus 1 can be written outside, minus 1 multiplied by k equals 0 to infinity. This k plus 1 goes away. I have 2 times minus 1 power k x power 2k plus 1 2 squared times 2 power 2k times k factorial times k plus 1 factorial. I can remove 1, 2.
K plus 1.
Sorry,
K1 of x is equal to the denominator term 2 to the power 2k plus 1. K1 of x.
oh, here,
You know, the second equation. Yeah, that thing. Second
yeah,
denominator 2 to the power 2k plus 1.
2 to the power 2k.
Because x is
Oh, yeah, we have a n here, right? So this is 2 power 2k plus 1. Remember, we have a 2k plus n here. So n equals 1, we'll make it 2 power 2k plus 1. So we can also write this 2 power 2k plus 1, which exactly compares with j1 of x. So you have this is equal to minus j1 of x, which proves j0 prime equal to minus j1. Okay, so one second. There is no big trick. You have to systematically start with the correct formula for Bessel's function, unlike me. Like, make sure you don't miss your n's and k's. Sometimes you will have to stare at that equation to identify patterns. There is no more tricks to that than any other new skill or theorem or anything. Okay? Yes.
It's like if we just like this, take the series and derivative. Make it.
That's fine too. I'm not going to be picky about it, but I like it this way. Yeah. Yeah.
Can we use that identity in the example, or do we have to derive it?
You don't have to derive anything. Whatever you don't have, whatever you can get away without deriving, I'm fine with it. Show me your skill about how you'll use it. Application. Yes.
Okay, so we use because in J naught of X in the series, if you take the derivative of the actual like infinite series, like let's say the first term would be
Yeah.
negative 2x over 4, which simplifies to negative x over 2. I don't see negative x over 2 and
that is all.
So that is because I left out a 1 here, like a 2 power 2 here, which is missing. That's me.
so if like you ask this in the exam, we can choose to instead do the derivative of the infinite series instead of what we just did here.
Yes,
Okay.
you can do that. For absolutely convergent infinite series, term by term differentiation is not a problem. For series that have conditional convergence or if they diverge, it is a problem. That's why I don't recommend it. Okay? That's why if you are able to show this in the general formula, it's better than doing it term by term. Okay, so now you have learned to work with Bessel's function for, I'm sorry, the solution to the Bessel's equation for any value of nu, which is not 0 and not difference is not an integer. And then you started with the special case of nu equals n, which is still not equal to 0. I'm sorry, nu equals n. We are still looking at properties of Bessel's function. The question of getting a general solution to a Bessel's equation is still hanging because over here you can write C1 j nu of x plus C2 j minus nu of x to be a general solution. But that trick won't work when you go to case 2 and 3, okay, for which you need what is called as Bessel's function of the second kind, which is like the process of deriving another linearly independent function, which is given in section 5.5. Now, I am asking you to self-study 5.5, but I am also telling you it won't appear on the exam. It will appear for your project. So if you have to do your project, you have to study 5.5, but not under a tense situation of an exam. Okay, that makes sense? I'm meeting you halfway, not on the exam, but for your project.
Then case two, we won't be on the example, we'll be on the project.
Yes, yes. If it appears in the exam, it will be only case one where it will be a distinct value of nu, which is a rational number or not an integer. All right, so now we want to look at some special properties of these functions. Firstly, I mean, there are two things that I want to mainly emphasize. What is this j nu of x? That is how to derive the Bessel's function for any value of nu, which is not necessarily an integer. We have 35 minutes. Let's see. All right. So when we did derive the solution, we had a 2m equals minus 1 power m a naught, okay, divided by 2 power 2m times m factorial m plus nu m minus 1 plus nu plus and so on 1 plus nu. And then what we wrote was y1 of x is equal to p1 j nu of x, where j nu of x equal to summation k runs from 0 to infinity or m runs from 0 to infinity minus 1 power m x power 2m plus nu divided by 2 power 2m, wait, yeah, 2 power 2m m factorial m plus nu up to 1 plus nu. Well, this can include a naught, okay, this still can include an a naught, and by choosing a naught equal to 1 over 2 power nu times gamma function of nu plus 1. Oh, a lot of terms. We are making a very peculiar choice of a naught equal to 1 over 2 power nu times gamma function of nu plus 1, which means you should know or you should be told what is this so-called gamma function, which if you haven't seen before, here's the definition. Gamma function evaluated at a value of nu plus 1 is defined as 0 to infinity e power minus t power nu dt. This is how it's defined, okay? And you can easily prove that gamma of nu plus 1 is nu times gamma of nu. You can easily prove this. If you know nu plus 1, you can get what is nu, and then easily show that identity by integration, okay? So by choosing a naught equal to this, you can write this is 1 over 2 power nu times gamma of nu, and you can keep on doing this, okay, which is equal to nu minus 1 times gamma of nu minus 1 and so on. You can do this process infinitely, and what you will end up with what you'll end up with is writing j nu of x is equal to x power nu summation m equals 0 to infinity minus 1 power m x power 2m 2 power 2m plus nu times m factorial times gamma plus, gamma function at m plus nu plus 1. This is for any value, any nu, and if nu happens to be an integer, you can check this reduces to Jn of x because gamma of m plus n plus 1 is equal to, can you try this? That is, shall we try this? Gamma of m plus n plus 1 is, if you use this identity, this would be m plus n times gamma of m plus n, which would be m plus n times m plus n minus 1, gamma of m plus n minus 1. Knowing that m and n are integers, you will eventually end up with m plus n minus 1, and so on up to 2, and then finally 1, which is nothing but m plus n factorial. If you know this formula and also understand what is gamma function, you have covered two cases. You have covered the case where nu is not 0 and its difference is not an integer, that case. You have also covered the case if nu is equal to an integer, that is also covered by the same formula if you understand how the gamma function works. Okay. But as far as our class is concerned, the emphasis is not on remembering things. I allow you to bring your sheets to class, to the exam. So my suggestion would be to have this formula along with the riders it comes with, and also have the formula for Jn of x. And if you have space, even write down the first few Bessel functions, J0, J1, J2, so that you can save some time during the exam. Yeah.
We also could have proved the identity using this formula, right?
Sure. I mean, this formula works for two cases, both general value of nu and integer value of nu. The only problem with this formula is it will not give you two independent basis functions when nu is an integer or 0. For that, you have to refer to the second kind. But as long as you are working with new values which are rational but not integral, you are golden. You have two basis functions, you can construct solutions. Like for example, this is one of the problems on one of the mock exams. X squared y double prime plus xy prime plus x squared minus 4 over 49 times y equal to 0. Construct a general solution for this Bessel's equation, where nu happens to be 2 over 7. And clearly 2 nu is not an integer. 2 times nu is not an integer. So the general solution would be y of x equals c1 j nu equals 2 by 7 of x plus c2 j nu equals minus 2 by 7 of x. Done. If you write down this one statement, you're done.
We would have to stand.
Well, you know what Bessel's function is. It's on your sheet. Why would I ask anything that's on your sheet? If you are able to write down this one statement, it means you understand what are basis functions. This will take you 30 seconds if you know what you're doing. Okay? You had a question? No? So I would generally encourage you to pay special attention to there is in page 191, there is a box which is labeled as theorem 1, page 191, theorem 1, it's in a box. It contains several identities involving derivatives of Bessel functions. I would focus on those. I would practice those. Okay, page 191. I would also practice the problems in problem set 5.4 because might as well say this. If you are going to get a Legendre's function problem, it's going to be to solve that equation. But as far as identities are concerned, we are going to focus heavily only on Bessel function. So I would practice all the identities and problems that appear in problem set 5.4. That would prepare you well for what you can expect in the exam. Okay, problem set 5.4. Don't ask me which problems. Do everything. Practice it. Let me ask this question. Suppose this is not x squared minus 4 over 49 and I had x squared minus 4, which makes nu equal to 2 or plus minus 2. U squared equal to 4, which means nu is plus minus 2. Would this still be applicable? True or false? It's not true or false. Would this still be applicable? Yeah.
First term is applicable, but the second one is not.
Because
The
so when you write Jn of x and j minus n of x, you multiply each with a constant. Is this a linearly independent solution? No, because Jn and j minus n are not linearly independent. You can check that. You can try evaluating what is Jn and what is j minus n, their ratio. You will actually find out that this is a constant. So this trick will not work if if nu is an integer. It will work only if nu is not an integer. Okay. So we talked a lot about integer and not an integer. There is also a special case where if nu is a half integer, we get certain special properties. So let's say, for example, we calculate for nu equals half, what is j half of x? Can you get that from this formula? So this is j to the power half, I'm sorry, x to the power half multiplied by m goes from 0 to infinity minus 1 power m x power 2m 2 power 2m plus half times m factorial times gamma of m plus 3 by 2. This is the starting point. Okay? Agreed? If I take this and substitute nu equals half. Okay, let me clear some space. So I'm going to write this I have a 2 power half here, I have a x power half. I'm going to write this square root of x over 2 and remove it from here. Okay. So if I expand this square root of x over 2, what is the first term? X power 0, which is 1. 2 power 0 again 1, 0 factorial. 1 divided by gamma of 3 by 2. You got to at least remember this property about gamma functions, and then what will happen? So if you have gamma of 3 by 2, this is gamma of 1 by 2 plus 1, which is half times gamma of half. You don't need to even be able to compute what is gamma function or evaluate the integral or anything. I might even provide this on the exam. Gamma of half is equal to square root of pi. You just need to know this fact and this identity. I'll give you this, but I won't give you this. Okay, so this is nothing but square root of pi over 2. Okay, not only is that important, look at the next term here. M equals 1. This will be minus x squared divided by 2 squared times 1 factorial is 1. M of 1 plus 3 by 2, which is 3 by 2 times gamma of 3 by 2, which is 3 by 2 times half of gamma of 1 by 2. In fact, if you are clever about this, it doesn't even matter that you know this fact. It's the fact, it's a common factor that's just going to come out of every term. You don't have to actually know that gamma of half is square root of pi. Okay, are you with me so far? Are you okay? Good. What is the third term? Can you write down? Plus x to the 4, 2 power 4, 2 factorial times gamma of 0, 1, 2. So this is 1 plus 5 by 2, which is 5 by 2 times gamma of 3 by 2, which is 5 by 2 times 3 by 2 times gamma of 1 by 2. Is that correct? No, this is
half.
sorry. This is m equals 2. So 1 plus 5 by 2, 7 by 2, which would be 5 by 2 times 5 by 2, which would be 3 by 2 times 3 by 2 times gamma of half, 5 by 2 times 3 by 2 times square root of pi. Am I doing this right?
No,
Because
3 by 2 plus half.
The correct. Okay. So you can write this down. That is, you can keep on writing more terms. What is the common factor here? So this is this if I may simplify, this is 3 by 2 times 1 by 2 times square root of pi. This is 1 by 2 times square root of pi. This term is going to be common in all of these. And of course, you are also going to get like a half term common. You may ask, what is the point of this exercise? The point of this exercise is, if you do some little simplification, you will find out that whenever nu takes values that are half integers, these infinite series can be identified as some elementary function. Turns out this would be cosine of x if we persist with a few more steps. Okay. What do you do next? So you can write square root of x over 2 divided by, this term is common, and then you're also going to, let's say this term is common. So you're going to get square root of pi over 2. So this becomes multiplied by 1 minus x squared divided by 2 squared divided by 2 squared multiplied by 3 plus x to the 4th divided by 2 power 4 multiplied by, multiplied by 3 over 2 multiplied by 5 over 2 times 3 over 2 times, so I'll have times 2 factorial. Plus and so on up to infinity. Sorry?
Yeah, I'm just seeing how the bottom thing with this. No,
Okay, this is going to take a few steps. So let's make sure I didn't make any mistakes so far. I guess what I'll say is, I don't think I'm very well prepared to talk about this today, but I would refer you to example 3. Example 3, which is in page 193. Page 193. So this is an exercise mostly that tells one fact, which is the values of nu which are half integer lead to elementary function. And where that becomes useful is when you are deriving analytical solutions and nu happens to be falling in that category, it allows you to simplify your solution quickly. Okay, so let's just leave it at that. I still have one more topic to just touch upon, and if time permits, maybe an example. So we took a long detour. Remember, I said that when nu is not an integer, it's easy to construct a general solution. So we write y of x equals C1 j nu of x plus C2 j minus nu of x when nu not an integer and 2 nu is not an integer.
Isn't the second one's efficient? We don't need, if you just say two, it's not an issue.
Well, you could still have nu equals half or nu equals 3/2. Or let's put it this way, if you have plus minus 3/2, you would still have this difference to be an integer. That's what I mean by 2 nu. The solution to your the solution to your indicial equation is always nu and minus nu. So when I say 2 nu, what I mean is nu minus nu is not an integer. This is the kind of general case. Now, what about constructing solutions when nu is in an integer? So I'll briefly touch upon section 5.5. For nu equal to n, an integer, okay, you would still write y of x equal to C1 Jn of x. That part of the basis function is still the same. And then we'll write C2 times Yn of x. Okay, C2 Yn of x, where Yn equal to, where Yn of x is the Bessel's function of the second kind of order n. What is this Yn? Yn of x may be written as 2/5 Jn of x multiplied by natural logarithm of x plus 2 plus gamma plus x power n over pi summation minus 1 power m minus 1 hm plus hm minus 1 divided by 2 power 2m plus n m factorial m plus n factorial x power 2m. You would have already figured out why this is not on the test. Minus x power minus n divided by pi this is the Bessel's function of second kind, has a rather lengthy formula, okay, which even in the book the derivation is not presented, it's skipped over. And this is given in page 199. So for your exam on Monday, of course, this is not something you need to worry about. But as you are starting to think about your project, which I think I made it due on October 30th, I suggested that you can pick any problem from problem 1 to 9 of problem set 5.5. Let me pick one example. Okay, problem 1. This is x squared y double prime plus xy prime plus x squared minus 16 times y equal to 0, nu equals plus minus 4, or you can say n equals plus minus 4. H is defined in that page, page 191, where hm is 1 plus half plus and so on up to 1 over m. Okay, so if you look at this, you can clearly say n equals 4 and minus 4 are your solutions. You would need Bessel's function of order, Bessel's function of order 4. Let's say n equals 4. You can also pick n equals 4 to get the second kind and construct this solution and then develop a program which will evaluate the coefficients according to this formula. It may look very onerous, but what you need to do is put a for loop and implement a calculation of this infinite series and this finite series. Remember, it goes from 0 to n minus 1. Just one question for you. I'm sure all of you have tried programming at this point, being graduate students. How do you calculate an infinite series in a computer program? How do you stop computing terms? When do you stop computing terms?
Well, you can say precision, so you can get your answer to like 3 decimal points if you want, and then once your answer is not changing by more, like the difference between the answers is not changing by more than 3 decimal points, so then you can stop there.
Okay. Any other responses?
We can't have a preset number of terms for your calculation.
Well, if you said preset, how do you know by say 6 terms that terms become negligible?
Yeah, so that adequately large number, like 50, 100. As long
That
as
is
you-
just wasting computing power. What he said is a much better approach in which you can say, you can add, like you can do this as a loop. Let's suppose you're calculating this summation, you can calculate once and twice and thrice and keep tracking of the sum. If the sum doesn't change after between the 30th iteration and 31st iteration, if there is no change, then you can stop. Okay, and what constitutes no change? You have to choose a tolerance. It could be 10 power minus 3, 10 power minus 6. It's a little subjective, but if you figure out how to implement an infinite series, which you can develop as a program, and just ask your program to calculate e power x at x equal to minus 1. You know this value, like point, so what's the value? 0.34. Whatever. We know the value, and you know this function is 1 plus x squared over 2 factorial plus x cube over 3 factorial and so on up to infinity. So you can compute 10 terms, 15 terms, and see at what number of terms you get a converged value. Okay, so check your program using a simple function for which you know the value, compute an infinite series, compute a finite series, and then add them together. So this is very basic programming skills. Yeah. So if you look at if you look at the problems 1 to 9, they are all given like this, but without boundary conditions. So you also need to assume some sensible boundary conditions. So I want you to think about it a little bit. What boundary condition will make sense for this type of Bessel's equation? I want you to think about. Okay, so that is your project, which you don't have to worry for Monday's exam. That said, last announcement, on Friday, I plan to hold like a problem solving session where I won't bring any agenda items. I will come here, and if you have any specific problems that you want me to try, or I can suggest examples, we can go over the mock exam, whatever you wish to do. Okay, just a quick poll, how many of you are actually planning to come?
The first 40 minutes.
Okay, this is a good number. More than half the class is planning to be there, so I hope you can come in person. Okay, I don't want to be talking at the camera. If I show up here only and 3 people are here, I'm serious, I won't do this. I don't want to be talking at the camera. I want people to come here so I can actually have a session and we can do this. Okay?
We could do a poll of hands, who plans to be here in person.
Sorry?
Can we do a poll of hands, who plans to be here in person then? Just good. Never mind.
No, it's come again.
I was saying, if you're worried about talking to the camera, we could do a poll of hands of who's planning to be here.
Yeah, in person. Who plans to be coming in person? Still almost the same number. Good. Okay. All right. So, to conclude, I would focus a lot more on Bessel's function than on Legendre's polynomial. Because as far as my understanding is concerned, if you understand this, you would be able to work with Legendre's polynomial easier. The other reason is when we do the chapter on PDEs, we'll focus a lot more on spherical PDEs. So you will get to do Legendre's polynomial again there also. Okay, so but for this time, let's focus more on Bessel function. Section 5.3, 5.4, I would really work out all the problems if you can. Okay, thank you.